Okay, can you hear me now? Okay, it looks like you can hear me. Well, thank you so much for catching that. Alrighty then. Well, the stream starts now. um, let's just do a quick recap. So last we left off here, I left all of you on a cliffhanger, and that is we were about to get to parsing assembly code. So today, what I'd like to do is go through parsing assembly code and possibly get at least to a cliffhanger of outputting some binary. So this is what I was working on here, and we've got some symbols. Um, we've got these comp statements, and this was the trickiest part because these comp statements would be actually fairly trivial to translate directly into binary. But I wanted to have an intermediate representation, so I had to think about how I would represent these, and in the process of that, like thinking about what constraints there are, like what exactly are the pieces of this comp. So we had to actually think about this as a little mini language and not just what it translates directly to. So we have all those pieces here, um, and we never got to actually testing it. So let's just fix this compilation error real quick. The final output here, we parse a destination. So a C instruction is a more complicated instruction, right? There's a comp piece, there's a dest for like where this is being saved to memory or a register. And then there is this jump effect. Um, and here, this comp.parse seems to be returning the wrong type. Yeah, okay. So let's take a look at that here. This just needs to return a comp, and that should be fine. Are all of those, in fact, comps? So const.0 is not a comp. Um, I suppose we could just make that. Or I suppose I could wrap that in a no-op. What's the point of wrapping it in a no-op? Wrapping it in a no-op also allows us just to have a register. It's like we could have like negative D, or we just have D or A. So that's what we'll do. Let's do um, no-op around each of those. In fact, let's just do cool. And this last case here also should be a no-op. The no-op also needs to extend comp. Here we go. Okay, the compiler's happy. So I think we can start testing this on individual lines. Okay. Um, this is a worksheet here. And I don't think I need that anymore. We'll just push that off screen. Um, so from here, I can import my stuff and run it interactively, right? So the thing we're testing is this cinst.parse. Well, thank you. I'm glad you find it relaxing. So we have cinst.parse. And what can we do? Let's do all of these from line one. So let's do at I and see what that returns. Handsome, welcome. Reg has no case with name. We're doing Nand2Tetris. So right now, we're converting, we're basically doing this that's on the screen here. This is an assembly program, and we want to turn it into binary. Hey, you're up early or very late. Welcome, good to see you. Okay, so we have an issue here. Enum reg has no case with name at I. Interesting. So I is not a eesh. Okay, let's not look at that yet. I just want to see it work properly on something. Let's try m equals 1. Can we parse that yet? Oh, wait, we need to parse from a string. Great. Okay, so we have a destination set, which is m, and no op is our computation, and there is no jump, hence the null here. Cool. Now this A instruction. Oh wait, no. We can't parse that because that's not C instruction. If we did A instruction, that parse, that should work. I'm not sure we've written that yet. Yeah, we haven't written A instruction parsing just yet. Okay, so that's our next step. We parse the A instructions, which should be a lot simpler than the C instructions. And just a refresher on the A instructions versus the C instructions. An A instruction, basically, you can give it a constant or a symbol, and it's basically saying load the A register with this value, or with the value that this symbol represents. So it's named the A register because this is usually used for addresses, but this is also the only way to get a constant into your program by placing it in that register. So this register is dual purpose. That's why here we have this xxx parameter as either constant or a symbol. So let's define a parse method here. And in here, I suppose we could try to parse it as a symbol first, and if it fails, I guess our symbol parsing needs to have a failure mode, not just throw. Or if we try to parse it as a constant first. Let's add a constant parsing method. So right now, constant just refers to an int, but really, these constants are going to be a little bit constrained. They are these values. Basically, it's a 15-bit unsigned int, or 15 bits, 15 zeros and ones. So when we parse that, we do want to have a constraint, which actually we've already done. You can see it right here in the code. Okay. So to parse this then, we're going to parse that raw string as a constant, and if that fails, we'll then try to parse it as a symbol. And we're just going to wrap this up in a try. And then if that doesn't work, we try to parse it as a symbol. it's not parsing n, we're parsing this raw string. Simple dot parse raw dot to option. Now, ideally, I just want to point out that I'm being sloppy here. Ideally, my parse methods here aren't just throwing these exceptions. I'll probably have these all return an option or an either, just to indicate that an error happened of some sort. But that's a kind of cleanup we will do later to refine things. I just want to get it running. So we do that, getter else that, and we wrap the whole thing. I suppose we just write it this way. Okay, that should compile. Parse raw, oh, this raw is a string. We need to try and parse that as an int. Okay, raw dot to int option. All right, so we're gonna take that n, and that's what we're gonna parse. So assuming it's a valid integer, we'll try to parse it that way. And I like it better this way because then that error is preserved. If it is a valid integer, but not a valid like 15-bit integer, then we'll still get an error. Otherwise, we try to parse the string as a symbol. So two options, and what's wrong here? This constant.parse should work on an int. Two option is not a member of int, sorry. Oh, right. Cool. Okay, so we have a parsing for our A instruction. Try to parse as an int, otherwise it's a symbol. And we have our parsing for a C instruction. And these are all just instructions in general. So let's go to our instruction. And we just parse as an A instruction, else a C instruction. And actually, how do we decide on that? We decide on that basically if it has the @ symbol in front. Yeah. Okay, so if raw that starts with an @ then we parse as an A instruction. Otherwise, it's a C instruction. Cool. Now, if we go back to our test worksheet, we should be able to start parsing things. Simple isn't label or var. So that @I wasn't parsed as a var, and that should be a var. What's a hack emulator? So in Nand2Tetris, hack is the name of the CPU architecture. So hack is like the assembly, the machine code, the CPU itself. And then later on, there will be Jack, which is the name of the programming language that is built on top of all of this later on. And how do I keep motivated after working all day? Uh, well, it's the other way around. This is what keeps me motivated to work all day because doing this is fun. Doing work is not so much. So I had this dream because I want to make programming like a bit more fun again, right? It's not the same when you're doing it as a software developer for some institution, right? Or at least it's not the same kind of fun. It can be fun. I know. Am I being too diplomatic there? So I think I just want to test that symbol parsing itself. Um, okay, so a symbol, right. A symbol doesn't necessarily have an at symbol in it. A symbol could mean any one of these things or the variable, yada yada. And a symbol can be used in a couple different contexts. So they can be used with an at, but I'm sure they can be used elsewhere. So like this label here, this label contains a symbol inside of it. Um, so that means when we're parsing our A instruction, we don't want to pass that at along to the symbol parsing. So in instruction to parse here, we want to strip off that A at some point. And I think it's fair to put that here. Let's do, I mean, I could also do it this way. And I can rethink it later. So we'll do this raw match case. So if it's at some xxx, then we're going to do an aints.parse that xxx, right? I don't actually want to put that here. We'll put that at the level of the we'll put that at the level of the instruction parsing itself. Okay. So any other case, I guess, is an error, which we'll just leave as a triple question mark not implemented for now. But otherwise, that xxx is a possible symbol or constant. So we're going to do that xxx to an option. And what's our issue here? We found an int or a symbol required in an A instruction. Right, that whole thing needs to be wrapped as an A instruction. Okay, back to our test worksheet. And an implementation is still missing. Let's go down a level. Let's go symbol.parse. Let's parse a symbol named I. Can we do that? Yeah, we can do that. And that parses correctly as a variable. So let's parse some other symbols that are possible. Something like loop. Now this should parse as a label. Okay, and symbol.parse, something like R3. Oh, that prints a symbol, but what that is a specific kind of symbol. It's a virtual register. So also like a hard-coded kind of thing. And the last kind of hard-coded thing, let's say like local. So the difference between these symbols, these variables are going to be assigned as needed. Their values are going to be assigned as needed. These labels are going to be assigned based on where they fall in the program, right? So this loop here will always refer to 4 because that's the address of the line that it's on. So that you can jump back to that address 4. R3 and local are both always going to be hard-coded because they refer to specific registers that are used for, that are reserved for specific purposes. Do I have any rules for using AI? When I use AI on the stream, it's usually just to complete boilerplate. But for the most part, I would like to create human-generated slop here. The fun in it here, I don't know, I can imagine vibe coding maybe a test suite. Not in this case. I don't think I want to do a vibe code a test suite for this. Um, Anywhere where it gets boilerplatey, that's where we'll use AI. But I'd like to be in the nitty gritty explaining every piece. So if we're doing AI, we can't really do that. Okay, so we can parse symbols just fine. Let's parse an A instruction. And let's parse one that's a constant. Or rather, let's start with the constant first. So constant.parse 1, 2, 3, 4. That should just show up as a number. Oh, right. You can parse a number directly, like 1, 2, 3, 4. Cool. All right. So when we parse this as an A instruction, there needs to be that at symbol there. And we'll strip this number and try to parse that as an int. We are not liking something here. Yeah, I very much agree about using AI. Sometimes it can generate a lot. I use it for work um, at a corporate level. And man, AI generated test suites aren't fun to mess with. Okay, we found a string required, a constant or a symbol. Oh, no, you're dot parsing here. Okay, and we're failing to parse. An implementation is missing. So that tells me, are we falling to this case? Let's just give this a proper error message. Okay. A instruction must start with an at symbol. Okay, so we are failing to parse that there. So this line here should be parsing and stripping away that at symbol. Otherwise, it falls to this case. So we're not even getting into this case here. Also, are we? Oh, we are recursively parsing here. We don't want that. And we're not symboled up parsing raw. We're going to parse that XXX bit. Okay, let's take a look at this again. Great. So in this case, it parsed that properly as an int. Now let's try to parse a symbol, like, I don't know, sum. Great. So this is an A instruction that refers to a symbol, namely sum. And I think with that, we can start parsing some lines from this program. Cool. Let's try another one. Let's try the loop label. Ooh, I think it's going to fail on this because we don't have those parens. And we actually don't have, I don't think we even have, like, say, white space handling. Cool. So at our top level parse, we do need to make it a little bit more sophisticated. Yeah, let's go there. So it's not just an A instruction or a C instruction. It is potentially a label. So let's match cases. We'll take the raw string and we'll strip all the white space. It is actually also potentially a comment. Yeah, an instruction is not potentially, actually, this is fine. Because a label is not an instruction. That's not the highest level thing we're parsing. The highest level thing we're parsing is a line. And a line is either an instruction or a comment or a label. You can only have one of the three choices per line. Oh my God, Lazy Schemer, welcome. Good to see you. It's been a while. Okay, so for our line then, let's define parse method. And I guess we have some raw string. And how do we do this? We'll strip for here, and then we'll match a few possible cases. So if it is starting with the slashes, then we have a comment. And we'll just leave that there as a string. I think I would actually like to, so I know my comment at the moment is just a type alias for string. But at some point I might I'd like to keep that information tagged. So I'm going to create a constructor. Object comment def apply. And this will eventually become an opaque type. So it's something that an opaque type is something that's secretly a string. It's kind of like a value type. Um, or a new type if you're from Haskell. So it's a type that is secretly a string, but can only be treated like a comment. It's not going to be interchangeable everywhere a string is allowed. So this returns a comment just by applying it there. Okay. And at some point, we'll have a cleanup. And we'll make these all a bit more strict. So there's our comments. I don't know. Okay, so there is the comment case. Let's look at the label case. So in the label case, there's parens, and then a label here. Let's name this comment. That's what it is. Now a label. What have we done with a label? It is a type of symbol. So label just with the name here. And then otherwise, we parse it as an A instruction or a C instruction, or rather, no case who anything else gets the inst.parse treatment. Okay. Or instruction, not parse rather. I'm going to rename our instruction just to inst. Okay, now we can parse an arbitrary line. Since I have instruction.parse, we can do, or rather, it's not even instruction anymore, it's just inst. We can do line.parse. And in this case, we have a label. Okay. Now we should be able to parse all the lines of this program. So I'm going to translate this program over from my example. Let me zoom in a little bit so everyone else can see what I'm working on. Okay. Right now I'm just going to transcribe it directly as a multi-line string. And we can try and make sense of this program as we're transcribing it. So first it's a comment, because what this program is doing is computing the sum from 1 all the way to R0. So R0 is being taken as a parameter, and that's saving the result in R1. So R0 and R1 are virtual registers. So take the value of the argument from R0, put the answer into R1. And then we have another comment saying we initialize I at 1. So this first at I is saying that we put the address of I. So I is a variable. It gets assigned some address arbitrarily. So our address assignment is going to start at 16 when we're building our symbol table. Because that's the end of the virtual registers. So this could just say at 16 here, but essentially it's saying save the value 16 to the A register. And then this m equals 1 is saying take the value in memory that's referred to, take the memory location referred to by the A register and set its value to 1. And we've got a comment sum equals 0. Okay, so now we have another variable named sum, and we're setting its value to 0, right? And then we're setting a label for our loop. This is where the loop starts. And then an explanation of the loop. If I is greater than R0, then we go to stop. All right. How is that expressed? So first we check the value of I by setting A to I with at I right here. And then we set the value of the D register. So we have two working registers that we can play with basically. It's the A register and the D register. The D is the data register. So in this case, we're saying D be the value of M, which is the location referenced by at I, right? And then we go to R0. So we're temporarily saving the value in D, the value of I in D. Then we go to R0 and we subtract the value of R0 from the value I, right? So we're doing a comparison. And then at stop. So this usage of at is different from the previous two because in these cases, we were referring to a memory location in RAM, right? This at I is like, it's pointing at a variable I. This is pointing at the value in the register R0. In this case, this is actually a memory address in ROM, which is stop down here further in the program. So that's going to refer to line 18. So where these two were RAM, this here is a ROM reference. So now for this ROM reference, we look at the value of D and we jump if that's greater than 0. Right? So D, after subtracting, and why are we doing that? So we have our R0, or we have our I value, right? Our loop value. And then R0 is our parameter. So let's say we were doing 1 to 10, right? And then we're saying I equals I minus 10. And while that's negative, we don't do anything. But as soon as it becomes greater than 0, we are going to jump. And the location we're going to jump to is this one right here that we had just set. So stop's going to have a value of 18. And we're going to end up jumping to the memory location 18. Yeah, let's keep walking through this. So there's another comment here, sum plus equals I. So as a reminder, actually, no need to remind anything. Let's keep going. So we look at our I value. We save that value to our data register. And then we look at a current sum value. We add that value, or we add the value in the data register to the sum. So M, which is the sum currently, becomes D plus M, where D is the current value of I, right? And the next step is to increment I. And we do that by referring to I and setting M to equal M plus 1. And then we go to this loop or we set we have a point to the loop address location, this right here. And we have an unconditional jump straight there. Great. And the final bit here, once we're done, we have our stop label. And we take this value of sum, and we set d equals m. Oh, why is it d equals m? Why is it not? Because it said computes R1. Shouldn't we be setting R1? Okay, we're temporarily saving. I think we're missing the rest of this program because we're temporarily saving the value of sum to d. And I think what we want to do next is do at R1, and then here set m equals d. That makes sense, right? Yeah, the book didn't show the rest of that program, but I think that's where it's going, yeah? Well, we can work with it. We can work with it. Anyway, we have the program transcribed. Let's test that we can parse all of those lines. So test program. Test program. And what? We want all the lines of that. Hey there, how's it going? Let's just take a look at our lines. Oops. What did I end up doing here? Okay. These are our lines. What we actually want to do with each of these is do a line.parse. Oh, we don't want that. Okay. So we'll call this our lines. And let's just take a look at them. It looks like it did parse successfully. And yeah, now we have actual things we can work with, right? So we have an A instruction, C instruction. This is a comment, etc., etc. Yeah, great. So from here, we can start working on turning that into binary. We're not actually going to go straight to binary. What we're going to do is go to an intermediate representation. So I have this ML package. ML meaning the machine language. So this is kind of a semantic representation of the binary. Let me pull up the diagram again, the relevant documentation. Okay, so that is going to be, I suppose, yeah, it's just a semantic representation of this, I suppose. Because there's a comp, there's a dest, and there's a jump. And what I've implemented here so far is a way to get all of these from binary. I haven't yet made a way to turn these to binary. But the first important piece is turning these from assembly into ML level instructions. So interestingly, at the machine level, at the machine layer, or at the machine language level, there's also a distinction between A instructions and C instructions, right? The binary here. So an A instruction always starts with a 0, and a C instruction starts with 111, followed by all these bits representing the computation that's happening. Um, yeah, and we are missing a step because in order to do this, we'll need to know what these symbols mean when we dereference them. So we do still need to go through a program like this, a list of lines, and create a symbol table. So we'll go back and do that. And then I think at the end, we can just take these and turn them to binary. And then see if it matches this sum 1 to n. Okay, so we have a test program that we're able to parse. And we will continue right here. I'm going to take a quick bathroom break. I'll be right back. And I will leave this on screen in case you're wanting to make sense of some of this while I'm gone. All right, we're back. So, building a symbol table. Part of me just wants to wing this. And I can refer to the book, but I want to puzzle through this. So let's look at all the possible symbols. Label is an easy one, right? Every label, you just look at where we are in the program. So I suppose as we're parsing lines, we'd count the number of instructions so far. So every time we have, so I suppose we need to have an assembler with state. Yeah, so we have an assembler with state, and we're counting the number of instructions. So here, 0, 1, 2, 3. We've had 4 instructions at this point. So this loop is referring to address number 4, right? So that's going to go into the symbol table like that. Now something like, say, R0, that's going to be hard-coded. So part of the symbol table is already going to be hard-coded. So I suppose I could have like a base symbol table that gives all of those values. And actually, I do already have values for a bunch of these. So for all my pre-def symbols, I do already have a value. So I guess our symbols again, our symbols are either pre-def symbols, which will already have a value, or they are labels, which will need to be assigned a value based on when the label appeared. And then there are variables, which I suppose will just be assigned a symbol in order. So here we have I and some, so starting from 16, we'll just assign them in order 16 and then 17. And so forth. And I know at some point we're going to build like a virtual machine on top of this, which is going to need to allocate like a lot more memory. And I kind of forget what happens there. So I'll be curious to revisit that when we get there. Okay. Anyway, symbol table. Program is a list of lines, right? Oh, we have a program as a list of instructions, actually. I think the lines themselves matter, because the lines could also be a loop. And we could have it consume one line at a time. Geez, do I want this to be something with state? I think I'm just gonna make this a function. Fold left. Okay, so a program is gonna be well, let's redefine program. A program is a list of line. Specifically, yeah. And we're gonna have some state. I don't know what to name this state. This is like this is like an assembly state, or like the assembler state. So there is the instruction count. Sparkly dark matter. Hello, welcome. So let's just do like I count, and we're gonna spell it out a little bit more so that the search function actually works. And there's gonna be a variable count, right? Is that all of our state? I might just represent that as a tuple. Okay. So we're gonna take a program dot hold left, and our state is those two plus the table. Yeah, so instruction count's gonna start at 0. Var count is gonna start at 0. And then table is gonna start as a map.empty of symbol to, I suppose we can say int, knowing that that int is actually an address. Interestingly, it's always either a ROM address or a RAM address. I'd kind of like to tag it with that information, but I'll resist that for now. Okay. So we have, how are we going to name them? Ints count, var count, and table. And then we have that along with a line. So in case of a label, in case of a label, then we add to the symbol table. So we're gonna keep our inst count and our var count, and we're gonna do table.updated. So we're just gonna look for a new triple. And just do this. Okay, if it is a label, then we're going to update the value at label to be, I guess it's exactly the instruction count. Right, at this point here, for this loop, for example, we've had 4 instructions, so the next instruction is going to be line 4. All right, that's handled. Now what if we have, what can a line be? A line is either a label instruction or a comment. Well, we might as well handle out the comments. In fact, let's put that in this first line here. So let's save this whole thing as state. In fact, we don't care anything about the state when it comes to the comments. So the triple is just called state. And the comment is a comment. And we just pass the state along, unchanged. Okay, and the final case is it's some sort of instruction. And we don't do anything based on the instruction itself, do we? Yeah, we ignore that. Mm. Well, actually, no. The instruction does matter. If it's an A instruction, and then that might be a new symbol, which needs to have an address assigned. So let's look specifically at A instruction. A instruction. And we'll look at the case when that is a symbol. Okay, so now the table here gets updated. Well, it depends actually. So if table that contains our symbol already, then nothing happens. We just pass along the state. Well, actually, the instruction count does increase. I'm going to start using a case class here, just so I can make things more semantic. So what kind of state transitions can we have? We can increase the count of instructions or variables. Def count inst. So we just copy inst count equals inst count plus 1, right? And def count bar. This is a case where I would like actually to have Copilot because it would autocomplete that pretty instantly. And I suppose we can also do like def associate. So we can associate symbol with an address. It is always an address, right? Yeah, and all of these return new states. So in this case, we just take our underlying table. Oh, we have a binary type here that we're using. I don't know where else we've used it. I guess it is binary. But what it is specifically, I mean, it's a valid address is what it has to be. I'm just gonna do this type alias set address equals int. And that's going to have a constraint. It's going to be like 0x0 all the way to 0x. The maximum, I guess, is 7FFF. We'll just add a to do there to do verify range. I'm not sure if that is actual range, but it has some sort of range. That's the point. So anytime we construct an address, we'll want to verify that. So address. Okay, so when we do an soak method, hold on, let me just change up my music a little bit. All right. All we're doing is updating this table. Table.updated, like we did down here. Symbol with that address. Right, actually, but we're copying the whole thing. So copy table equals. Cool. We can write this up a little bit differently. So when we have a comment, the state remains unchanged completely. When we have a label, we're going to take our state, and our state is not triple anymore. We can just wrap this whole thing up. So state and we don't need to give that type anymore. So there's a starting state. Oh, you know what? To do starting state with hard-coded values, maybe. Okay, so now we can say that when there's a comment, we just pass the state along unchanged. Otherwise, if there's a label, then we do state and we change it by doing a soak. So we're associating a symbol, which is a label, with the address given by the instruction count, state.instCount. There we go. Yeah, that's a lot more clear, I hope. And now here, in the case of an A instruction that is a symbol and not a constant, then we're going to do a conditional. So if this table already contains the symbol, then we just pass along the state. But we do increment, not count instruction, right? Otherwise, okay, so otherwise, state.table contains. Otherwise, we take the states. Let's give that a triple question mark for a second so it goes back to compiling. Otherwise, we need to add that symbol from that A instruction in as well. So otherwise, we're still going to count the instruction, .count instruction, and we're going to associate this new symbol with, I suppose we could do, if we're starting at 16, we could do 16 plus the number of variables so far with 16 plus var count plus a state variable count. Yeah. And then we're also we're also adding to the variable count. So state, we're going to count the instruction. We're going to count the variable. And then we're going to associate that variable with this value given by the variable count. Okay, I'm happy with that. I think that at the end will give us a state that has a symbol table. I'll state equals that, sure. Oops. Okay, after all that, we're just going to turn state.table. And let's see what we get. And actually, what's the issue here? Oh, we do still have some missing cases. Okay, so missing cases. Case if we have a state with any other instruction at all, then we are still going to count that instruction. State.count instruction. Yeah. And I'm noticing something here. This actually just falls down to this case. So I'm going to add a guard up here. So if we have an A instruction with a symbol, and if a state.table that contains said symbol, then we fall into that whole case. So we can just remove that if else statement because we can put it as part of the pattern match itself. Okay, otherwise, if it's any other instruction, we still add to the instruction count. All right, that's compiling. Let's see if we can get that to work. Give me a sec here to fix my green screen. All right. Well, here is a moment of truth. So here's a program, right? Well, we still need to parse as a program. So this is a program, right? I guess we need like a program parse. We have a line.parse. We don't have a program.parse. But a program.parse would essentially just do this here. But we do have a program. Now let's do symbol table for this test program is a string version. What do we call that? Like the raw program. Anyway. And what do we have? So we have loop going to 16, and we have stop going to 18. No. Loop should be going to 4. And also, we're missing like all of the variables. Right? Like there are variables in here for sure. Yeah, like this one here. Well, program is a list of like that should be an A instruction. Oh wait, no, that's a comment. This is an A instruction with the var I. So then why is it? Let's go back. So when we have an A instruction, oh, up here, we use instruction count. Right. That seems about right. So say for loop, we would use instruction count of 4. And here, we use a variable count. I mean, assuming that this is a variable, I suppose. Yeah, this wouldn't be any symbol. This would have to be a variable specifically. We'll continue to call it sim, but it's actually going to be a var. Because if it's any other symbol, like here at loop was already going to be, well, mentioning at loop is not going to define it. This label statement here with the parens defines it. Okay, let's try that again. See if we get a different result. Okay, great. Now loop points to 4 and stop points to 18. We did seem to forget to assign variables themselves, so these label statements work. Aha, this if is backwards. If not state.table, it contains sim. Okay. Great. Now I points to 16. Sum points to 17. Great. Loop points to 4. Stop points to 18. Etc., etc. Cool. And then now we can transform a program using a symbol table. So before that, let's just make a program.parse function. We'll basically use this line here. Okay, so where did we define program? So we have a def parse, raw is string, multi-line string. And we're gonna take that raw and we're gonna take its lines to a list and map the line.parse. Okay, and we can construct a symbol table. And the final step is still to, well, we want to dereference everything still. So deref, we'll need that symbol table. And when we deref, basically we're going to take every A instruction and translate it. So we deref a program with a given symbol table. And we're going to get a new program with only constants in place of these variables, in place of all these references. So program.map, and each of these are going to be some line. And we're going to match left, ref. And this line could be a comment, in which case we just pass that line along, etc., etc. Not a legal formal parameter for a function literal. Oh, you know what? We can just do, we don't need to do this line match. Okay. If the line is a comment, we just pass that line along. If it is a label, we also do nothing. Actually, the only case we really care about, so case A instruction, specifically when it's a symbol, we're going to turn it into a new A instruction with a constant. There are two kinds of symbols. So there are some pre-def symbols. Let's handle those first. So pre-def symbol. And instead we do a inst of pre-def sim.value, which gives us a constant. Great. And the other case we care about is any other symbol. Yeah, it's a variable or a label. And in that case, we look it up in a table. So table sim. And we say that's a constant. And otherwise, any other line just gets translated as is. Excellent. Let's try that out. So let's see what our program's looking like. So we have, okay, we have our test program. I'm going to rename this. This is our raw test program. Or, no, it's like the source of our test program. Test program source. Okay, so program.parse test program source. And I need a symbol table for that. Table. Well, actually. Okay, so we parse a program, we get our table. And then dereferenced, I guess transformed program. And it's going to just be deref program given that table. Okay, and let's take a look at that. Okay. Well, I don't like that. That doesn't look very transformed to me. Also, I need to get like 2 string methods for each of these, so that this displays a little bit nicer. Because this looks kind of exactly like program. If you did program for each print line, doesn't look like any transformation is going on there. Yeah, and var I, and this one also starts with, oh, actually, no, this is different. And 16. There's no var. Cool. And 17. Okay, great. No, every time there's an and instruction, it is actually replaced with a number. Cool, cool. We're so close. And it's only 9:30. I think we are going to get all the way to binary tonight. Okay, so once we have a transformed program, we can start outputting binary. Okay, so we have this deref method. And I guess, let's see, we need to turn our program to ML. To ML from some arbitrary program, right? So we want to do everything we've done so far. And I guess this is going to be an ml.program, whatever that is. Let's define that first. Let's go to our ML package. Type program is just going to be a list of instructions, I suppose. Yeah. Oh, sorry, my key bindings are going a little bit whack here. Okay, a list of instruction. So this is going to return an ml.program from an assembly.program. So we're going to take the lines of our program and map over them. Program. Actually, we want to deref and all of that. So val table equals symbol table of the program. And we got deref the program. And then we're going to map those lines. Yeah. And there are going to be a few different cases. So comments are going to get ignored, for example. So case. I suppose I could just filter all of those out first, since they don't translate directly into anything. Also, the labels at this point are now useless, right? Because we've dereferenced any usage of them. So I think we want to filter it for A instructions and C instructions. I think we can merge our map and filter into one statement in the collect. So we don't care about comments. We don't care about labels. At this point, we only care about instructions. So let's start with a instruction. And in fact, I'm going to add a check here. Because if there's a symbol at this point, then this is an error. Program not referenced. Okay. My goal eventually to make this not compile. My goal eventually, like this kind of thing, shouldn't be like an error you should have to catch. That should just not be allowed by the type system. You reference the program using the table, actually. Okay. But if we have an A instruction with a constant, then we're going to do some ML instructions. ML.AINST with just the binary, which is just an address. Pretty straightforward. So the C instruction is where it gets interesting. So dest comp and jump. So we have an ml.c instruction. Okay, how is that comp translated? Let's do that last, actually. Oh, thank you for the autocomplete. Okay, so let's start with the dest. Here, this dest is a set of registers. So those registers are going to be A, D, and M. And I'm going to zoom in over here, because depending on which of A, D, and M are set, we'll have these binary set. So I think I should make a helper function here somewhere. Actually, what does a dest look like over here? Because we're actually not going to go straight to binary. So in our ML package, let's look up a dest. Oh yeah, it's just going to be this ADM, a triple boolean. Okay. We'll just do this as simply as possible. So we have an ml.dest, and A equals dest.contains reg.a. Yeah. And same for the other two. Okay. And now our jump. What does a jump look like? It is one of these 8 specific cases. And the jump we are working with is what exactly? Oh, is this the same kind of thing in the assembly? Okay, we have some redundancy, I feel like. We don't need to have 2 different representations of a jump, do we? Yeah, that can just be a shared model. So the difference here between these two jump models is that this one parses from a string. This one here parses from binary. It does also go to binary. Yeesh. Okay. I'm going to sidestep that discussion for now by doing the simple, easy answer. And we're just going to say this is a ml.jump.ordinal. And since the ordinals match, we can just do jump.ordinal. We'll just match the enums against each other. And add a little note to do this is hacky. Slash redundant. Okay. I just want to get that out of the way because the interesting part is comp. And in the ML package, comp is just all of these flags. And in our package here, a comp, well, we'll see. Just in ml.comp. From mem. How do we know if it's from mem? We can do comp dot. Well, I think we have to look. We have to look at our C instruction comp here. Okay, so we have to disassemble our comp a little bit because from mem depends on whether. So we have a statement like, well, where are our comp statements? Like one of these here, right? And the from mem version is basically saying we're doing m+1 instead of a+1. So if the left side, actually, all these plus statements are not the same. So like these increment all these unary operations, we can just look at if that arg is m, then it is from mem. And there are some cases where I suppose it's undefined. Like say 0. For example, here, it doesn't actually matter whether a equals 0 or 1. You're going to have the same result, which is 0. So it looks like to me that the convention is just to say that it's not from memory, unless making it from memory is actually going to unless it's actually going to be used from memory in like a material way. So if the left argument, well, actually in a binary operation like add, this left argument is always going to be the D register, right? You have like D minus A, D plus A, or whatever. So in a binary operation, if the right side is an M, then we can say it's from memory. Okay. I think to make this a little bit easier for myself, I'm just going to have binary ops and unary ops explicitly marked. Or you know what? I think I want a help function for something like this. So let's say def from, so our comp has a helper method here that says from mem boolean. So we have a case like add, and it doesn't matter what left is, but if right is an m, then yes, right? And that's true for any binary operation. Okay. Let's add a binop. And a binop needs to have a left and a right. So all of these now extends binop. So if you have any binop, or just binop, then we check op.right equals reg.m. Okay. And in the case of a unary operation, just fix the capitalization here. Okay, and then we have a sealed trait unop extends comp, and then def arg is a register. So these are all unary operations. And in the case of a unary operation, just check op.arg equals reg.m. Okay, and then what's the other case that might matter? I suppose we have a no op. That works kind of like a unary operation. Except that's not necessarily a unary operation on like a register. So we'll have that as a special case. So case no op r reg, and we'll just say r equals reg.m. And in anything else, it's just false. I suppose we could just say true here. So we have reg.m, just say true. Otherwise false. Okay. Unary op. Okay, we have the helper that we need. So we can just do comp.from mem. Great. Now 0x, eesh. When do we zero out the x, basically? So just to explain that a little bit, I want to bring your attention to this diagram here. And this is an explanation of these comp opcodes. So XXYY, the ALU of the hacked machine operates on two inputs. So there's an X and a Y. This F for the function changes whether you're doing addition or a bitwise ANDing. And this NO says, do we negate the output? And by negate, I mean like binary negate flip. So here, ZX means do we zero the X? Do we negate the X? Do we zero the Y? Do we negate the Y? And based on various combinations of doing those, you're able to implement stuff like addition and subtraction and negation, whatever, by having some flip-flop of all of those bits. And now we get to reconstruct that. Geesh. And I think we almost just want to handle these kind of case by case. Like match on different cases. Like, I don't know if I want to handle like 0x for every possibility, or for each possibility, just handle those 6 bits. I think for each possibility, I actually just want to handle those 6 bits. Let's do this. Well, ML comp. So we're going to do our comp and match. I'll comment this out for now. We have an issue here. We have a comp, we have a dest, we have a jump. Okay. So I suppose we have, let's start with the no ops, I suppose, because that includes the constants. So we'll take that arg and we'll match it. So if it's any register, actually, what do all of these have in common? Well, D, for example. So we turn the second argument to 0 by having 1, 1 here, which is to say we negate and we flip it. Or like we zero it out. We zero it out and then we negate it. Why do we do that? So essentially becomes like -1, right? Let me make sense of that real quick. I won't go that deep into all of them. I just want to use this as an example. So here we have 0, which means we're just adding, right? Oh, we're ANDing. Okay. So, like here, if we're getting x by ANDing with a bunch of 1s, when we AND with a bunch of 1s, we still just get the same result. It becomes an identity function. Geez, that's a little bit convoluted. I guess you do have to have two arguments. And that's how you would do identity, is you just like AND against a bunch of ones. Okay, so this 1 over here gives a bunch of ones, and we AND against it. Okay, so case, we have A, we have D, and M. From M is the same for all of these. I guess so this is false. And then are we zeroing X in the case of an A? Yeah, X is like the D argument. So 0, X is true. Negate X. Just fill this out. All right. So we have ADM, and then we have 1, 0, and -1. I don't love this. Surely there's a cleaner way to. I know this is something that'll probably wake me up in the middle of the night, and I'll realize it's something stupid easy. But if anyone's watching and has ideas, you are very welcome to chime in and be like, "Hey, you don't have to like boilerplate all of this." Okay, so if we are doing D, then in this case, we're going to AND against. So false. We're going to 0 the Y, and we're going to negate the Y. True. True. And we're not going to do anything to 0. You know what? I at least need a builder, like a comp builder, where like everything defaults to false, and then we just say the things that we are doing. Basically, I want to be able to say, or here, I'll show you the syntax I want. I want to be able to say for reg m, ml.comp, and we'll say from mem. This is going to be from memory, and we're going to negate x dot 0x, and then we are going to AND, right? Because that's how you do it. So I'm going to make myself a tiny little DSL for putting all these instructions together. That way we're not just saying all these flags, because this is super hard to read, isn't it? Right? Yeah, that's definitely not a controversial idea. Right, another little rabbit hole. And I predict, like we're getting so close, we're probably gonna get to getting this comp representation, and we might not get to binary tonight, so we might end up with another cliffhanger. Okay, so we need a comp constructor. So we're gonna have like just an apply method, which is gonna give us a default comp. Um, and it's just gonna be false all the way down. Right. And now we'll add some transformers here to comp. So def from mem, or we could say like we're dereferencing it. I like from mem. So this dot copy from mem equals true. Def neg x, this dot copy negate x equals true. We'll also have 0x. I'll copy paste those for the y case. And let's do an add. Well, let's see, add is all already. Let's say and. So it's add normally. We never really have to say add. We could say adding or anding. Adding. Is that copy add equals true? Right. And def anding is that copy add equals false. And then def neg out is that copy negate out equals true. I guess I could just say negate. Yeah. Oh, I guess we do have to give from mem a different name. Let's call it dereferencing. We're gonna dereference it. And I guess 0x and 0y we can't use. Um, what's a good name for that? I suppose what I could do is for these, I use the flag names. Right? ZX, NX. It's not gonna like that until I fix it. Okay, do we have... Let's just fix some compilation errors so that we could actually work on this. I'm gonna comment these out. And we have an issue here. Should be fine. Not found type constant. Oh, I don't like that. Don't need that import there. Label? What happened to label? Did I accidentally delete a bunch of things? No, it's all there. Okay, we'll start at the top of the errors. I suppose we can't have a forward reference on the type. That's strange. I thought no, you can have a forward reference. It was compiling not that long ago. Okay, so last label example. Just putting this up here, fix that. Case class label extend symbol. Can't find symbol. Sorry, I think it's actually freaking out at something else. Let me just the bit I was working on. Let's comment that out. So this whole toML function, let's just comment this whole thing out because we're not going to use it just yet. I just want everything else compiling while I make my little mini DSL. Cool, I think it's happy again. Everything's compiling. Yeah, okay, I had some issue there that was making it hard to parse. And these are not in my file, so we're good. All right, back to this case here. This is now ZX. This is NX. ZY. NY. This is F. And this is NO. And I suppose this is just A. Yeah. Okay, so now we can name this from mem. And when it's from mem, we set A equal to true. 0x, 0y, negate x, negate y, adding, anding. And let me just add the documentation here for that f plus or and. So if f and, okay, plus if true, otherwise, yeah. If true, add, else, and set it that way. Okay, I think that should do me well enough. Okay, now we go back here. So we have a table, we dereference that. We have some mystery comp that we are not filling out just yet. We have a dest, we have a jump. Okay, and this is how we're defining the comp. Comp match case. So we still have to match this argument. And now we can change the right-hand side of all of these cases. Let's start with a bare comp for all of these. And actually, let's give that basic comp a better name than just apply. Because that 000 case is actually going to be like a basic add, I guess. It's like the add both slash and both case. Yeah, let's just call it the default. I don't know why it's default, but or yeah, we can give it a better name later. But let's start with that comp dot default. Okay. Or it's kind of like an empty comp, right? Like following other convention. Great. Value and is not a member because we said default from m.negx 0x dot and. We don't have an and. We have an and-ing. Yeah, we can just call them add and end actually. Okay. Negx 0x. Negx and 0x combined actually do have a meaning. When you're both negating x and then zeroing x, what you're actually doing is making x a bunch of ones. Which is to say, like, you're making it -1. You're saying x is -1. Let's add that in there. So let's add some bigger constructors here. Def x neg1 equals this dot neg x dot 0x. Well, let's say that in the opposite order. 0x and then neg x. And then let's do the same for y. So if y is -1, 0y and -y. Okay, and let's look at some other cases. Interestingly, that doesn't actually match on to I guess here's the case where we're adding. Or we're adding. We're adding -1 to 0. So like this would be like neg x add 0y. And that sort of works. Cool. That's nice semantics. And what's going on when we do one? When we do one, we just negate the whole output afterwards. Cool. So from mem, we x neg 1. And then just y. I guess we could give it a little bit of semantics here and say like def x. So if we're just going to use x as itself, then we say this copy zx equals false, nx equals false, right? So I guess we could call it like use x. At some point, like this is a little bit like gratuitous, but it is like the kind of thing we could do. It's not like it is over engineering. I'll admit that we don't need a fancy DSL for that, but I'd like to be able to say to do just m, then we take x negative 1 and wait, why is x negative 1? And use y. Yeah, and we're ANDing it with y. I should just like y and x better. So we would say like y dot from m and x as negative 1. Cool. So in that case, like a is just going to be y and x negative 1. Whoops. But it's not from them, right? That's the only difference. Let's say it the other way. X negative 1 and y. Yeah. Okay, okay. That's a little bit gratuitous, but I like how it reads. So in this case, we have just x and y neg 1, right? For the d. Okay, now how then do you get 1? We can think about this without actually looking at the chart now. We have enough language here. So to get 1, you're going to add I suppose you could add negative 1, negated 1. Remember when I say negate, we're like talking about 2's complement negate. So when I say negate 1, we're actually getting negative 2. So to get 1, I think let's just plus 0. Or no. We can get a 0. We can negate a 0. So we can get a -1 by negating a 0, right? So to get a 1, I suppose we can negate okay, so to take a unary negation here, we flip the sign and then subtract 1, right? We're doing that to like -1. We flip the sign to 1 and subtract 1. So to get 1, we have -1, and we're going to flip that one. No, not quite. We're going to add first. And then we're going to negate that. Cool. So we're going to take x -1, add y -1, and then negate the whole thing. And that's how we get 1. To get 0, we just 0 them both and then add, right? So 0x. Oh wait, these are going to be the constants, right? Okay, so we're going to 0x, add 0y. Yeah, we're still missing some cases. We'll get there eventually. And if we want to just do -1, geez, if we want to do -1, what can we, oh, we can get there from 0. So we add 2 zeros together, and then we negate that, right? 0 plus 0, negate to get -1. 0x to add 0y, and then negate all of that. Cool. And we can check ourselves against the book. So here, in the case for 1, we do negate x. We -1 to x, we -1 to y. We are adding, and then we're negating the whole thing at the end. They are not negating at the end for -1 and 0, though. I guess there was a simpler way to do -1. So here, they're doing -1 on the x, adding 0. Oh, and then we're just ending it. No, we're just adding 0. Okay, so what I had said was a little bit roundabout. I think I did. Okay, we're looking at -1. Okay, if you look at this here, 0x, 0y, and then negate. So 0, 0, negate. What I could have just done was -1 plus 0, And then don't, wait, no. -1 plus 0. We're doing this. Right, we're negating a 0. Which is to say we're doing -1 plus 0. Yeah, that actually makes perfect sense. So we say x -1, add 0y, and then we don't need to negate at the end. Makes perfect sense. 0x add 0y, x -1 add 0y. And to get 1, it's a little bit roundabout because you need to add both of those and then negate again at the end. Cool. Yeah. Okay, this might take me a hot minute to get the rest, but let's see. So we handled the no op. What other cases do we still need to handle? Case, I don't know, let's just do binary ops in general. Or let's look at our op definitions. So we have an add. Let's do an add. I think we have like a parsing issue here. So like in these cases, left is always going to be D, isn't it? Anything else is like a mistake. So we can only really add D and D with A and M, right? I don't like writing this whole nl.comp at default, so I'll find a way to shorten that eventually. When we're adding, I guess we're just taking it as is. We're just taking x.add.y. And then in the other case, we're just doing that same thing, except we are doing it from mem. Yeah. I do like this semantically. So now we have an and it's basically the same thing, except we and right there. Now a sub is a little bit more complicated. There's going to be this duplication here where the only difference between these two lines is based on what that second argument was. So I kind of want to factor that out, but for now, I'll just read it more explicitly. And for these, like, we know that those must be D. I'll just add a note to do assert left is. Actually, I think I already had something like that written somewhere. Comp left side is 0 or D. Yeah. These bind ops. I'm going as a to do. Left is always D. Right. we can try it as an assertion, some test. Okay, so for all of these, you can just leave that blank. And yeah, we'll leave those in there for now. Now, if we're subtracting, let's just start with reg.a. So in order to subtract, what do we have to do? It's a little bit roundabout. Let me just look at it here. So if we want to subtract, say like d minus a or a minus d, actually kind of goes both ways. Ah. Yeah, okay, the left side isn't always a d, is it? I mean, x is always referring to d. That much is for sure. But the way we express it here, the way we're allowed to express an assembly does allow us to place d on the right side, like in this a minus d. So let's start with reg.d. If we're doing d minus a, then we do add, but we add the negated x. Wait, we negate x, add that to the a, and then we negate the whole output. We negate the one that we're not using. Right, so just to show you in binary what that looks like. So let's say we're doing 7 minus 5, right? Then what's actually going on here is we're doing 7. We have the 7 and the 5. We're negating the 7, and we're negating the whole thing. And that gets us to, that's how we subtract. Okay, so in this case, if we're doing d minus a, then we're gonna neg x dot add y, and then negate the whole thing, right? And if we're doing a minus d, then we just do the opposite. So we make y, add x, and then negate the whole thing. And then we have the versions of that that are from memory. Dot from mem. Okay. And I don't know. I don't want to permit anyone to write a plus d. I'd rather they just wrote d plus m. And the only person using this is me, so I won't permit myself. But I do need to fix what I said about these add cases here and add, which is always D, and add and add. Okay. Now we do the same kind of thing with our and or. So let's start with and. Oh wait, actually we already did and. And was straightforward. Let's also do or. And for or, I'm going to refer to the manual. It's a fun exercise to think about it. So if you want to like pause and think about it, you're welcome to, but I'm just going to look it up here. So if we're doing an or, then wait, we're just ending after negating them. Negate them both and then negate the whole thing. So we neg x and neg y, and then negate the whole thing. And when it's an m, we do dot from mem at the end. Okay. And you know what, just for good measure, so that we catch every case, let's just do any binop. So if we have like add or and or, with a D on the right side, then we just swap them. Or, I don't know, to do maybe normalize operand order with respect to D. We'll leave that as a to do. Okay, that's almost all the things. So we have and, we have or, we have all the binary operations. Now we just need to increment, decrement, negate, and not. Okay, we can do all of those. So case, let's start with not. That's going to be super simple. So we have any register. And it actually does depend on what register we're using. So we have to use all cases. So reg.d. And in this case, we have ml.com. And I really want to shorten this whole thing. For now, I'm just going to write like an MLC for this whole mlcomp.default. Now MLC equals ml.comp.default. And we can give it a better name when I think of it, or when someone else thinks of it. Okay. Okay, so if it's not registered D, then we neg x, and I guess I guess we can just zero out y. I think we must zero out y actually, because something could be coming from y. Um, 0 y. Actually, we need to neg 1 y, neg 1 because we're going to add it. Neg x and y neg 1. So once we've negated x, we flip to bits, and if we AND it with a bunch of 1s, that does nothing, right? So we just get that neg x. Okay, case not, and if it's reg.m, we are going to need a test suite for all of this. Let's start with A, actually. A. So it's going to be the same kind of idea, except with what? Flip x and y. So we're going to say x neg 1, or let's say neg y, and x neg 1. And we do the same thing for m, except we do it from m. And just to verify here, so the not cases, right? We have a neg 1, we have a neg 1, and then, wait, we negate at the end. Yes, we do negate at the end because we are ANDing with a bunch of 1s. I'm sure there's something in here that I've messed up. But the nice thing about the way I've written this is that it'll be somewhat easy to debug once we have a test suite that can see those bugs. Great. How about negating a number? It's kind of the same thing, except that you're not adding, isn't it? Yeah, it kind of is. So let me replace that with neg. Whoops. We're just gonna add. I really do want to collapse these A and M cases together across all of these cases. And I'm thinking of a nice way to do that, but that might be a back burner, wake up in the middle of the night kind of a thing. What is remaining? So we've got neg, we've got not, we've got decrement and increment. So +1 and -1. And that looks differently depending on what you're +1ing to. Okay. So let's do this. We have inc the 3 registers. All right. So let's say we're incrementing D. So to add 1, add 7, right? We negate, we add actually hold on, let's negative 0. So if we add -1 to that, -7 plus and then negate that. There we go. That's how we get 8. So we just negate, negate, negate. Okay, so we neg our x, and then we're adding to y -1. And then we negate from there. Cool. And we do the same kind of thing. Except backwards. So for the A case, we're gonna neg y, add x -1, and then negate the whole thing. And for the M case, I'm gonna do that, but I'm gonna do it from mem. Okay, and now decrementing. So if you want to get 7 to 6, I think we do it that way. Yep, plus -1. Okay, so we just have our normal x, and we add y -1, and nothing else, right? And then for this, it's y to add x -1. And for this, it's that same thing, but from mem. And are we there yet? We're so close. Incrementing, decrementing, negating, nodding, and we have all of the no ops. That is it. Okay, so we can turn comp. Yeah, it thinks the match is not exhaustive. It is exhaustive, but that's a thing we can fix later. And we just pass that comp in. Wait, what? Acquired an ML comp. ASM comp. So this ML comp. There should be an ML comp. Oh, right. ML comp right here. ML comp. Okay. We can do it. We can turn a program to ML. Now we just do a toString on a machine language instruction, and we've got binary. We can do that in 10 minutes. We can do that in 5 minutes. So we're gonna have a payoff. So first, let's go back to our test. And we have a transform thing, right? We can dereference it. And what's this new? It's 2ML for a given program. We take the symbol table, we dereference it. We handle all these cases. Okay. So we have a 2ML. And we just pass in the program. Let's do it for each print line. Well, okay, look at that. That's basically binary. One more step. So we're gonna do what we want to be able to do is mlprogram.map.toBinary for each print line. And that toBinary is what we have to define. So we have an instruction F2 binary. Equals this match. Am I rocking a crazy mechanical board with the funky switches? No, I'm not. But I am opinionated about my keyboards. See, my keyboards must have a little nipple. I just can't use a I can't use a keyboard otherwise. I don't like using a mouse. I don't know. If I could get this as a mechanical keyboard, I mean I could. It's just you have to shop, takes effort, whatever. This is already available. Anyway, we are turning this to binary. Okay, so case if this is an inst. Okay, so what does an A instruction look like in binary? It's a 0 followed by all the bits of that. So I'm gonna AND it. And we're gonna AND that with 0x7ff. So we're only taking those 15 bits, making sure. I mean, I think it's all. That mask might be redundant. I'm not sure. I'm not sure if it's redundant or not. This is why we need types. N is an int, as far as I know. It's actually a binary, but the point of having this be binary is that we don't have to keep doing these redundant safe masks. So it's going to take that N, and we're going to do two binary string. Actually, we want to format it. How do you format? Scala format binary string padding. What's like 02B or something? Um, zero padded 8s. No. I don't want to. There's a built-in like formatting here. A built-in format. Formatting expression. There's like an interpolator. Anyone who uses Java knows what it is. Like this kind of thing. Yeah. Great. Except as binary. I guess we have to do two binary string. That way, there has to be a format that exists already, specifically for binary. I'm looking for these formatting strings. Okay, whatever, I'll work with that. Oops. Okay. So let's say we have a number like 5. Presents your, what does this do? Right, that just pads to 8. Let's say we do it to 16. And what does the X mean? Okay, so we're going to just do f5.to binary string. Wait, what? 5.2. Oh, wait, that only works with numbers specifically. Does the X mean like hexadecimal? Yeah, I've never had these formatting things memorized. Maybe I do want hex output, actually. There's no B, but I actually do think I want hex output. Okay, so let's do 4x, right? So if you have a number like 0x7ff, yeah, okay, we'll do that. We don't get binary tonight, but we do get hex. We'll just define like a little show for okay, what did we choose to do? Valorand %04x. %04x. Okay. Show and I guess this is actually gonna be 2 hex. And this is inside of instruction. All right, so other cases. Case, we have a C instruction. And with a C instruction, we start with 3 ones. So we're going to construct the number. So we're going to do the prefix val pre. It's going to be 111. And then how many is this? This is 6 plus 6, 13. 14, 15, 16. Yeah. So we have 7 times 2. We have 14, which is E. 0x E 000. Right? Dot to binary string. I just want those 3 leading ones. So those are pre-bits of our comp bits. Let's see. I think we basically take this whole array What's a nice way to do that? That fits. Okay, so we're going to take like true values. If A and one else. I know. I'm just going to rush through this with something, and we can refine it next stream. Bit boolean, and it's just going to give me an int, a single bit. If B, then 1 else 0. I guess there would have been true dot to int. Might work. No. Okay. So we get a bit. So we're going to take each of these and move them some number. So bit of A, and we're going to shift that left 7. Actually, this gets shifted 0. So that gets shifted 6. 6. And yeah, we're just going to sum all of those. I'm sure there's a better way to do this I'm not currently thinking of. But I'm beyond thinking right now. And we have an F, and we have this NO. 5, 4, 3, 2, 1, 0. And we take that sum. Okay. So those are just the bits. So we're going to take comp.bits, and we're shifting that left 6. And then we have the desc bits. So I guess A, D, and M can be 1, 2, and 4, and we just add those. Yeah. So list, and we have this dot. What's the leftmost? The leftmost is A. Dot A. If that's dot A, then 1, 2, then 4, that's 0. If that's dot, what's the second one? D. Yeah, D. 2 out 0. If that's dot M, then 1 out 0. And we take the sum of that. And we shift that over just 3 bits. And for the jump, we can just take the ordinal, I believe, because I already had them kind of in order. Right. So jump dot ordinal. I'll jump bits equals that. Okay, and to get the 2 hex of the whole thing, we gotta take pre-bits, and we're just gonna OR all of these together. Oh, actually, these should have been. No, I think adding this is fine. We can double check later. So we have pre-bits, and we're gonna OR it with comp bits, OR that with test bits, or that would jump bits. And that's all of our bits. And then to get our hex, I'm just going to show bits. And now we have a 2-hex function. And we have a little moment of truth because there's 2 hex. Cool. We have a thing. We got binary. We got binary output. Now, whether or not it's correct, we don't know. I could be lying to you. But we have a result. I'm telling you, yeah. I'm just asserting that these hex bits are that exactly. And I suppose, I don't know, I suppose I could have done that 2 binary string instead. But I'm not going to sit on stream and compare the individual bits. Not yet. That's going to be for next stream. We found a good ending point. Ugh. All right. Well, thanks everyone for stopping by. Yeah, next stream, machine that we're simulating. So that will be fun to go into like a new concrete level. In the meantime, let's find someone to raid. Yeah, hey, thank you. What is hack? You're asking right at the end. Hack. It is the name of the computer architecture that Nand2Tetris runs on. Nand2Tetris is a really fun project. You should look it up. You basically start with logic gates and go all the way to building a computer on top of that, and a compiler and whatever. And hack is just the name of the architecture. So it's like the whole first half, and then the second half is a language called Jack. And anyone got a stream, a raid recommendation here? No. I don't know a lot of these people. It's better than Whack and Crack. I guess we could come up with worse names. I don't know. It could be like Crack, Sack, Whack, Mac, Whack. Gee, I really don't know who to write here. Okay, maybe I just call it a night. But thanks, everyone. I'll just do a quick search because I'm doing assembly. All right. And I'll be back on again every week at 8 p.m. every Tuesday, 8 p.m. Eastern Time.